to start a new video on ratios, rates, and proportions. I think I can do it in 4 videos. First video will just be on ratios, second video will be on rates, and then the last 2 videos I think I can do on proportions. So let's see what we have here. Okay, for those of you that don't know, a ratio is a comparison of 2 quantities. Oops. Now, in the next video, we'll talk about rates. And rates are a special type of ratio where you're comparing 2 different quantities. So you could compare, for example, miles to hours, dollars to hours. You can compare dogs to cats. You're comparing 2 separate things. Much more generically in this video, we're going to be comparing just 2 ratios that have the same type of unit, or 2 ratios. We're going to compare 2 quantities that have the same type of units. Okay, so we'll compare dollars to dollars, cookies to cookies, brownies to brownies. Okay, again, the next video will focus on what to do when those units are different. Now, there are 3 ways to represent a ratio. All right. The first way you can represent a ratio is in words. Whoops, I meant quotation marks there, bless my heart. So I could say something like, Fred has 10 toys to Maggie's 12 toys. All right, so just a little brief statement. We're comparing 2 kids and the number of toys they have. Fred has 10 toys, Maggie has 12 toys. All right. So the second way we could represent a ratio is using a colon. So when you're using a colon, you kind of take the story away from the ratio and you just look at the numbers. So we have 10 toys to 12 toys. And oftentimes you'll see it just written as 10 to 12. So like when those units are the same, oftentimes you don't include the units in the representation with a colon or the next representation I'm going to show you. So when you have words, you'll generally see those units there. But for the second 2 methods for representing a ratio, you generally get rid of the units if they're the same. It's like we know we're comparing toys, we don't need to write it twice. The third way that we're going to represent a ratio is with a fraction. Now, I teach math, so I'm going to focus on the mathematical representation for a ratio. So I would write it 10 toys to 12 toys. And again, we already know that when you have a fraction, if you have something in the top and bottom part of the fraction that is the same, you'll oftentimes cancel it out. So just like in the previous example, we don't really need the units. We know we're comparing toys. We're simply interested in the numbers. Now, this example is unique because, well, it's not really unique. This is going to be fairly standard. But if you look at 10 and 12, as far as reducing a fraction goes, we know that we would reduce this fraction. So I could take this even further. I noticed that 10 and 12 have a 2 in common. So I could actually write this as 5/6. And this would be the most simplified form of that ratio. So this would mean for every 5 toys that Fred has, Maggie would end up with 6 toys. And this is going to be our goal. We want to get to the simplest form of a ratio. So a couple of things to know. We will first convert to fraction form. So if the ratio is given to you and it is not in fraction form, that's your first step. Take the information, write it as a fraction. And then the second thing we want to do is completely simplify. Now, completely simplify means a couple of things. No common factors, no decimals. And then this is the weird part. You're going to write your answer as a simplified fraction, but the numerator, and denominator cannot be fractions or mixed numbers. So that might not make sense right now, but I will show you examples where you have a ratio where the numerator and or the denominator would be a fraction or a mixed number all on its own. We need to simplify that out. And then there's one more really super duper important thing that I need to mention. Never write your final answer as a mixed number or whole number. A lot of times when we are dealing with ratios, our final answer might be an improper fraction. Leave it improper. Do not ever convert it to a mixed number when you're dealing with ratios. Also, sometimes your improper fraction could be an improper fraction where the denominator is 1. Ordinarily, if we were dealing with just plain old boring fractions, if we got something like 5/1, we would just simplify that to 5. But in this case, you don't. You want to leave it as 5/1 because remember, the ratio is a comparison of two quantities. We need to make sure our final answer shows that comparison of two distinct quantities, okay? So let's look at a few examples of how we would simplify these. So the first one is super duper easy. We have $15 to $17. We're comparing dollars to dollars. We do not need to include the units. So I would put my first number over my second number, and I would look to see if I could reduce. Well, 15 and 17 have no common factors, so that's my final answer. It's that simple. Next up, let's say we had 21 cookies to 28 cookies. Sorry, my penmanship is the pits today. All right, so we're dealing with comparing one set of cookies to another set of cookies. We know we're talking cookies to cookies. We do not need to include the actual unit of cookies in our answer. So I'm going to write this as 21 over 28. And then we want to see if we could reduce. Well, it just so happens that 21 and 28 have a 7 in common. So I'm going to divide numerator and denominator by 7. Well, 21 divided by 7 is 3. 28 divided by 7 is 4. So that just means for every 3 cookies in the first set, I would have 4 cookies in the second set. This is the most simplified ratio. Next up, let's say we're comparing lengths. I am really having a hard time with my penmanship today. Let's see if I can stabilize. Okay, so let's say we have 40 inches to 25 inches. So we could be comparing two different lengths of the same figure. We could be comparing two lengths of different objects. Doesn't matter. 40 inches to 25 inches. We're comparing inches to inches. So I would put 40 over 25. I noticed that 40 and 25 are both divisible by 5. All right. So 40 divided by 5 is 8. 25 divided by 5 is 5. And let's go back one slide. Over here where I said never, I'm like down here. Never write your final answer as a mixed number or a whole number. That's what's happening right here. Our final answer is an improper fraction, and we want to keep it an improper fraction. If we were to write this as 1 3/5, we've completely lost our comparison. We want to keep this 8 to 5. For every 8 inches in the first figure, I would have 5 inches in the second figure. So 8/5. All right, let's look at another one. Let's say we have 30 days to 10 days. You can come up with a scenario if you want. One person at a firm has collected 30 days of vacation. Somebody else has collected 10 days of vacation. It doesn't matter. We're comparing days to days. So I'm going to go ahead and start with 30 to 10, or 30 over 10. 30 and 10 both end in 0. That means they're divisible by 10. So I would end up getting 3 over 1. And just like the previous example, this is one of those situations where I said never write your answer as a mixed number or a whole number. Well, a lot of times if you're just dealing with fractions, if you ended up getting something like 3 over 1, you would just write it as 3. 3 divided by 1 is 3, but that's not what you want to do here. We want to maintain that comparison of two quantities. So let's say we go back to that situation where people have collected vacation days. For every 3 days the first person had collected, the second person had only collected 1 day. Let's try another one. Let's say we just have 185 to 60. Okay, so this example is written in that colon form. All right, we do want to go ahead and convert it to a fraction. So I'm going to take the first. I am really struggling with my handwriting today. We're going to take the first, put it over the second, and both numbers end in 0 or 5. So that tells me right off the bat that these two numbers are at least divisible by 5. So let's see what happens when we divide each by 5. Well, 185 divided by 5 is 37. 60 divided by 5 is 12. And that would be our final answer. I forgot to convert back to black ink. All right, so 37 twelfths. Again, do not write it as a mixed number. Leave it 37 over 12. What about this one? 400 to 550. Well, we start the same way, 400 over 550. Now, these numbers both end in 0, so we could say that they're divisible by 5s. We could say they're divisible by 10s. You could also, if you wanted to go higher, you could say they were divisible by 50s. Let's just keep it simple, and we're going to divide each by 10 for now, and we'll see what happens. Well, 400 divided by 10 is 40. 550 divided by 10 is 55. Still not fully simplified. Both numbers end in 0 and 5, so we know they're at least divisible by 5. So 40 divided by 5 is 8. 55 divided by 5 is 11. And now you have something that's fully simplified, 8 to 11. So whatever we're dealing with, let's say we were dealing with dollars. For every $400 in one set, there are $550 in the next set. If we simplified that, we could say for every $8 in the first set, there were $11 in the second set. Let's do maybe 2 more, and then we're going to start looking at how to deal with ratios that contain decimals and how to deal with ratios that contain fractions or mixed numbers. And then we can look at a couple of application problems. So let's say I have 65 to 90. I start by putting 65 over 90. Both numbers are divisible by at least 5. They end in 0s and 5s. So let's start there. So divide by 5. Well, 65 divided by 5, I believe, is 13. 90 divided by 5 is 18. 13 and 18 have no common factors, so there's your simplified ratio. Let's say we're talking dog treats. One box of dog treats has 65 treats. The other box has 90 treats. So if we wanted to simplify this, for every 13 treats in the first box, the second box would have 18 treats. One last example, 77 to 88. Write it in fraction form. Both of these numbers are divisible by 11. So we want to divide that 11 out. We get 7 to 8. So let's say one class at a school has 77 students. The next class has 88 students. We're comparing students to students. But to simplify that, we could say for every 7 students in the first class, there are 8 students in the second class. So that's simplifying really basic ratios. So what we want to look at now is how to simplify ratios that contain decimals. So simplifying. Woo, I'm having a hard time today. So really having a hard time. Simplifying ratios that contain decimals. This is sort of a weird thing for students, but it's worth understanding and it's worth knowing. So let's look at an example. Let's say I have 1.5 to 2.5. I'm going to go ahead and write it in fraction form. Now, we can't really do anything until we remove this decimal. Yes, you could cheat and you could go straight to your calculator and divide, but that's no fun. All right, so instead what we want to do is we want to eliminate the decimals from the initial ratio and then simplify, okay? So recall, and this would have been back in the decimal series of videos, If you multiply a decimal by a power of 10, it moves the decimal either to the left or to the right, depending on the power of 10. So if I wanted to move the decimal one time to the right, I would multiply it by 10. If I wanted to multiply the decimal by 100, it would move the decimal to the right twice. So let me just show you a quick example. So let's say I have 4.75 times 10. That's going to equal 47.5. If I have 4.75 times 100, that's going to equal 475. If I had 4.75 times 1,000, whoops, I would get 4750, so I'd get 4,750. So for each zero in your power of 10, it's going to move the decimal one time for each zero to the right. So in this first example, 1.5 over 2.5, I want to go ahead and multiply top and bottom by 10. Now, here's the thing that you have to remember. You have to multiply the top and bottom by the same power of 10, okay? Because this right here now is just a weird form of 1. All right, 10 divided by 10 equals 1. And if you go way back to like the very first series of videos, we found that when you multiply by 1, nothing really happens. In fact, 1 is called the multiplicative identity. It means if you multiply anything by that number, nothing happens. So what's happening here, it's a very weird way for this to happen, but we're not changing the value of 1.5 divided by 2.5. We're just changing the appearance to make it useful to us. So I multiply top and bottom by 10. I get 15 over 25. And if you don't believe me, take 1.5 divided by 2.5, and then take 15 divided by 2.5, put both of them in the calculator, and you will get the same value, okay? In fact, you'll get 0.6 and 0.6, okay? So again, we haven't changed the value of the ratio, we've changed the appearance of the ratio. And now that we have whole numbers, this is now something that we can reduce by hand. So 15 and 25 are both divisible by 5. So we would get 3/5. All right, and if you don't believe it, put 3/5 into your calculator and you're going to get 0.6 again. Okay, so we haven't changed the value of the ratio 1.5 to 2.5. We've simply changed its appearance. We've simplified it. We've taken those decimals out. Let's look at another example. Let's say I have 2.1 over 28. Well, in this case, the numerator is the only value that has a decimal, but I can't just fix the numerator. I have to multiply the numerator and denominator by the same value. We already know that multiplying by 10, where it's got 1 0, will move my decimal one place to the right. So I want to go ahead and multiply the top by 10. That's going to get me 21. But if I multiply the top by 10 and I don't multiply the bottom by 10, I have officially changed the value of the ratio. So I need to go ahead and multiply the denominator by 10 again. So really what we've done is we've multiplied this ratio by a weird version of 1. And now I've got 21 to 280. All right. So I know that 21 and 28 are both divisible by 7. So let's go ahead and say that 280 is going to be divisible by 7 as well. So I'm going to divide by 7. I'm going to divide by 7. And I'm going to get 3 over 40. So there you have it. It may not look any more simplified than 2.1 over 28, but 3/40 still equals 2.1 over 28. It's just simplified. We've removed that decimal from the problem. So if you don't believe me, 3 divided by 40 is 0.075. 21 divided by 280 is 0.075. And 2.1 divided by 28 is 0.075. So again, we have not changed the value of any of these ratios. They all represent the same amount. They just look different. Let's do another one. Let's say I have 4.5 over 1.25. Now this one's a little bit different. Both the numerator and denominator have decimals, but they have a different number of decimal places. The first number has 1 decimal place. The second number, the denominator, has 2 decimal places. Well, if we go back here, we could see that if I multiply by 100, which has 2 zeros, that moves my decimal 2 places to the right. I have to at least multiply by 100 because of this denominator. If I were to only multiply by 10, top and bottom, I would get 45 over 12.5, which still has a decimal. That's not what we want. We want to get rid of all of the decimal places, and we want to do it all at once. So let's go ahead and multiply top and bottom by 100. Still really just a weird version of 1. 100 divided by 100 is 1. We already know that multiplying by 1 doesn't change the value of what we're dealing with. So what we're going to end up with is 450 over 125. All right. Now we can go ahead and simplify here. I know that if I end in 50s and 25s, I'm at least divisible by 25. So 450 divided by 25 is 18. Let me go ahead and show that. $125 divided by 25 is 5. So our final answer here is 18/5. And if you don't believe me, 18 divided by 5 is 3.6. 450 divided by 125 is 3.6. 4.5 divided by 1.25 is 3.6. So again, we haven't changed the overall value of these numbers here, here, and here. We've just changed the appearance. And the one that we like the most is 18/5. It's the most simplified. All right. Let's do a few more examples just to make sure we're totally good on clearing decimals, and then we'll look at clearing fractions. Okay, let me get black again. All right, so let's say I have 2 over 4.6. Well, I've got 1 decimal place in the denominator, so that's going to tell me to multiply top and bottom by 10. Remember, that's just a weird version of 1. So I'm going to get 20 over 46. Now, 20 and 46 are both at least divisible by 2. They're both even, so let's start there. So we're going to get 10 over 23, and that would be our final answer. Again, if you don't believe it, check it. 2 divided by 4.6 is 0.43478, blah, blah, blah. 20 divided by 46 is 0.43478, blah, blah, blah. 10 divided by 23 is 0.43478,260, blah, blah, blah. They're the exact same value. So again, we haven't changed the value, simply the appearance. Okay, let's look at 0.2 over 1.8. All right, so we've got 1 decimal place in the top and the bottom. So we multiply by 10. So it's going to give us 2 over 18. Well, 2 and 18 are both divisible by 2, so I'm going to divide by 2, top and bottom, and that's going to give me 1/9. Again, if you don't believe it, check 0.2 divided by 1.8, 2 divided by 18, 1 divided by 9, you'll get the same value. One last example, let's say we have 0.81 over 0.9. Well, in this case, I need to get rid of 2 decimal places, so I'm going to multiply top and bottom by 100. That's going to give me 81 over 90. And I know that 81 and 90 are both divisible by 9. So I'm going to divide both parts by 9, and I'm going to get 9/10. And there you have it. So simplifying a ratio where you have decimals within the numerator or denominator, not really hard, takes a couple of steps. I do want you to practice this method though. Don't just cheat and go straight to your calculator. Practice and understand this method, okay? Now, next up, we want to know how to simplify where the numerator and denominator contain fractions or mixed numbers. So simplifying ratios that contain, fractions or mixed numbers. I think it's best if I just show you how to do this, okay? So let's say that we have, I think I like this one. So let's say we have 8.5 to 21.25. It's going to look weird, but the first thing we want to do is write this in fraction form. And then the next thing I'm going to do is I'm going to convert my mixed numbers to improper fractions. This is something that you might have remembered from back when you were dealing with fractions and mixed numbers, just in general, adding, subtracting, multiplying, and dividing. When multiplying and dividing mixed numbers, you had to convert them to improper fractions. And the same thing is going to be true here, because what we're really going to do is just divide. So to convert a mixed number to an improper fraction, you take the denominator and multiply it by the whole number. So 2 times 8 is 16. You add the numerator, so we're going to get 17 halves. And then for the denominator, 21 and 1/4, 4 times 21 is 84, plus the numerator of 1 is 85 fourths. So we get 17 and a half over 85, or whoa, I said that wrong. We get 17 halves divided by 85 fourths. So what we're going to do is we're going to take this very temporarily out of its fraction form, and we're just going to divide. Remember, this fraction bar simply means divide. So what I really have is 17 halves divided by 85 fourths. And hopefully you'll remember from dividing fractions that you leave the first fraction the same, and then you multiply by the reciprocal of the second fraction, right? So we want to look to see if we could simplify anything. Right off the bat, most people are going to notice the 2 and the 4. The 2 and 4 are divisible by 2. 2 divided by 2 is 1. 4 divided by 2 is 2. Now, the one you may not know is 17 and 85 actually have a common factor of 17. So 17 goes into itself once, and it goes into 85 5 times. So if we clean everything up, we get 1 times 2 over 1 times 5. So this fraction will actually simplify to 2/5. So we started out with something kind of wacky, 8.5 compared to 21 and 1/4. And once we go through the motions to simplify, we really just have 2 to 5. So let's try another one. Let's say I have 15 and a third, and I'm going to compare it to 3 and 5/6. So you can go ahead and convert to improper fractions now, or you can put this in a fraction and then convert to improper fractions. It doesn't really matter. So let's say we wanted to go ahead and convert to improper fractions. For 15 and a third, I would get 3 times 15 is 45, plus 1 is 46. You leave the fraction, or you leave the denominator alone. For 3 and 5/6, I get 3 times 6 is 18. 18 plus 5 is what, 23? So I get 23/6. You can go ahead and write this in fraction form if you want. Some of you will realize that you can kind of take a little shortcut here. But if you want to, go ahead and write it in fraction form. Remember, this line here means divide. So we really have 46 thirds divided by 23/6. And what we remember is we keep the 46 thirds, and then we multiply by the reciprocal of the second fraction. And then we simplify. 3 and 6 have a 3 in common. So 3 into itself is 1, into 6 is 2. 23 and 46 have a 23 in common. So 23 goes into itself once, into 6 twice. We simplify. 2 times 2 is 4. 1 times 1 is 1. And do not write this as plain old boring 4. Remember, this was a comparison of two quantities. So for every 15 and a third compared to every 3 and 5/6, we would really just get 4 to 1. Okay. So do not write this as 4. Write it as 4 to 1, or 4 over 1. Let's do another one. So let's say I have 5.5 to 9 and 1/6. So same deal. You can just jump straight to the division if you want. You can write it in fraction form. It's really up to you. Just be very careful, methodical, show your work. So if you want to, we can go ahead and write this as improper fractions and start the division. So for 5.5, I would get 2 times 5 is 10, plus 1 is 11. So I get 11 halves. And I'm just going to jump straight to division. For 9 and 1/6, 9 and 6 is 54, plus 1 is 55. All right, so what we really have here is 11 halves divided by 55 over 6. I'm kind of jumping from here straight to here, okay? So first fraction stays the same, and then we multiply by the reciprocal of the second fraction. So Now we want to cancel common factors top to bottom. 2 and 6 have a 2 in common. 2 into itself is 1. 2 into 6 is 3. 11 and 55 have an 11 in common. 11 into itself is 1. 11 into 55 is 5. Multiply across, I get 1 times 3 over 1 times 5. My final answer is 3/5. So you start out with something crazy, 5.5 to 9 and 1/6, but it really just simplifies to 3/5. Okay. One more, and we'll move to a couple of application problems. Let's say I have, maybe I want to do this one, 9 1/2 to 11 7/8. So let's go ahead and convert to improper fractions. 9 times 2 is 18, plus 1 is 19. So I get 19 halves. And let's go ahead and just jump to the division like I did in the previous example. And then for 11 7/8, 8 times 11 is 88. 88 plus 7 is 95. All right, so I get 95 eighths. First fraction stays the same, and then you multiply by the reciprocal of the second fraction. So let's see here. 95 divided by 19. All right, so first of all, we want to reduce common factors. So 2 and 8 kind of are the obvious one. They have a 2 in common. So 2 into 2 is 1. 2 into 8 is 4. And then 19 and 95 happen to have a 19 in common. 19 goes into itself once, into 95 5 times. We multiply across and we get 1 times 4 over 1 times 5. This simplifies to 4/5. Okay, so even though 9 1/2 to 11 7/8 seems kind of crazy, if we were to simplify it down, for every 4 that we have in the first set, we would have 5 in the second set. All right, so that's how you would simplify. If we go back briefly, we know that a ratio is a comparison of two quantities. You can write this in words using a colon or fractions. And since I teach math, I use the fractions. What you do is you convert to fraction form, completely simplify. That means no common factors, no decimals, no fractions or mixed numbers in the numerator or denominator, and never write your final answer as a mixed number or a whole number. We did some really basic examples where we were just dealing with integer values or whole number values. We then did some weird examples with decimals. And then we did some examples with fractions and mixed numbers. All right. So what I want to do now is a few application problems. Okay. So a lot of times you'll have a ratio and rate problem, or in this case, we'll just say ratio problem. And they're really not hard, but it's kind of hidden within a story problem. And sometimes those extra words just make the problem seem complicated when really it's not so bad. So let's look at one. The side of a building measures 105 feet long by 110 feet high. All right. So then the question will say, find the ratio of the height of the building to the building's perimeter. All right, there are two really important things going on here. There is a ratio and there's also a geometry problem. We need to find the perimeter, okay? So perimeter is not something that we've necessarily talked about much at this point, but I can show you pretty quickly. Now, for this building, we're saying it's 105 feet long, 110 feet high. The perimeter, all you have to do is take twice the length and add twice the width. So if we said the length of the building was 110 and the height of the building, or the width of the building, was 105 rather, then you just take 2 times the length, 2 times the width. And that kind of makes sense, because if this side right here is 110, then the side opposite it would have to also be 110. If this length right here, this side is 105, the side opposite it would be the same thing. So when you're finding the perimeter, you're just looking at the distance around the figure. So you're going to take 110 and add it twice, 105 and add it twice, or you take the shortcut, 2 times the length plus 2 times the width. So 2 times 110 is 220. 2 times 105 is 210. So the final perimeter of this building is going to be 430 feet. All right, so that is the first thing you have to figure out. They did not give us the perimeter of the building, but they gave us enough information to find it. Now for the ratio. They want the ratio of the height of the building to the perimeter. Well, what was the height of the building? We were told that the ratio has, or that the building has a length of 105 feet and a height of 110 feet. So the height of the building is 110. And then we need the perimeter of the building, which we found down here to be 430. And now we want to simplify this. So 110 and 430, they both end in 0. So that means they're at least divisible by 10. So I would get 11 over 43. 11 and 43, that's as simple as it's going to get. So basically, for every 11 feet in height, there are 43 feet in the perimeter. All right, and that's it. So classic word problem involving ratios, had that extra step of having to find perimeter. Finding perimeter of a rectangle, not too bad. Let's look at another one. So there were 85 women and 80 men at a town hall meeting. Find the following. We want to find the ratio of men to total people. We want to find the ratio of women to total people present. And then finally, we want to find the ratio of men to women. So we're going to find ratios in all 3 of these. So first thing I want to do is figure out how many people were present. So I'm going to do that right here. We had 85 women plus 80 men. So we were going to have 165 people total at this meeting, okay? So if we want to find the ratio of men to total present, well, there were 80 men. There were 165 present. So we divide each of these at least by 5, because I know if a number ends in 0 or 5, it's divisible by 5. All right. So 80 divided by 5 is 16. 165 divided by 5 is 33. I forgot to go back to my black color for the marker, but this right here would be your final answer. All right. For every 16 men that were at this meeting, there were 33 total. Let's do the same thing for women. Now, there were 85 women present and total 165 people. So we divide by 5 again. Well, 85 divided by 5 is going to be 17. 165 divided by 5 is still 33. So for every 17 women present, there were 33 people in total. Now, finally, I'm going to move the men to women over here just because I'm a little bit out of room. Now, there were 80 men total. There were 85 women total. So if I wanted to find the ratio of men to women, we would have, well, 80 divided by 5 is 16. 85 divided by 5 is 17. So that means for every 16 men, there were 17 women. And in this case, you're really kind of finding rates because you're dealing with different units, but you can see it works just like all the other problems. Let's do 2 more problems. So a particular company has stores in 18 states. Find the ratio of states with stores to states without stores. Now, every semester when I teach ratios and rates, there's always a question that comes up with the states in the US. So question, how many states are in the US? It's a shocking number of people that don't know this answer, okay? So a little bit of information. There are 50 states total. Okay, you need to know that. We are given that 18 states have stores. What we are not given is the number of states that do not have stores, but this is easy to find. If 18 states have stores, 50 minus 18 would represent the number of states that don't have stores. So that tells me there are 32 states without stores. All right, so we're going to answer the question. We want the ratio of states with stores to the ratio of states without stores. So there are 18 states with stores, 32 states without stores. We would want to simplify. These are both even, so you can see that they're at least divisible by 2, so we can start there. Well, 18 divided by 2 is 9. 32 divided by 2 is 16. 16 and 9 have no common factors. So for every 9 states that do have stores, there would be 16 states that don't have stores. All right. So again, just always know there are 50 states in the US, and it's shocking how many people don't know that. One more example, and we'll wrap up this video. Okay. So a town has 6 specialty shops. The following table shows total sales for 2020. So we have the store. We're just going to say it's 1, 2, 3, 4, 5, 6, and total sales. We have 140,000. We have 295,000, 560,000, 700,000, 795,000, and finally 980,000 in sales. So I could ask you tons of questions based on this table. I could ask you the ratio of a particular store to the total sales for all 6 stores. I could ask you for ratios between any 2 pairs of stores, and that's what I'm going to do in this case. Find the ratio of sales for store 5 to store 1. So basically we want the sales for store 5 over the sales for store 1. So store 5 had sales of 795,000. Store 1 had sales of 140,000. Now these are both divisible by at least 1,000. So we're going to get 795 over 140. I'm going to bring this down here where I have a little more room. And we're just going to divide piece by piece. So they both end in 5 or 0. So I know they're divisible by 5. So let's see, 795 divided by 5 is 159. 140 divided by 5 is 28. I think that's probably as reduced as it's going to get, but let's see. That is as reduced as it's going to get. So basically what we could say is for every $159 that store 5 makes, store 1 only makes $28. So let me go ahead and write that in words so you can see it. For every $159 that store 5 made, store 1 only made, whoops, I'm out of room down there, $28. And that's it. All right. So that's ratios. Next video, we will talk about rates. And remember, rates are really just a ratio, but in this case, they're going to have different units. And some of these word problems really were technically kind of rate problems, but they work the same way. So the next video, we'll talk about rates, unit rates, and unit prices. And then after that, we'll learn what proportions are, how to solve a proportion, and then we'll do problem solving with proportions. Okay, so this is video 1 out of 4. Good luck.